Welcome back, students. The next series of lectures here will be covering some important concepts of a geographic perspective, right? Big ideas that are essential to the field of geography, all right? So big ideas that have a lot of things sort of included within them. We're going to start with the idea of location and how geographers make sense of location. But we're going to move on in the next lectures to talk about things like place, the interactions between humans and the environment, ideas like movement and regions or regionalization, the kind of grouping of space, and how all those ideas relate to the field of geography. So starting here with the idea of location, the geographic situation of people and things. One of the ways we'll talk about location is as mathematical location, or sometimes you'll see it referred to as absolute location. This is in contrast to relative location, right? Remember that relative location is your location relative to the location of something else, right? It's kind of like saying things like, you get to my house by taking a left on the 2nd Street past that McDonald's on the corner, or something like that, right? My home's location relative to a McDonald's. Mathematical location or absolute location is much more specific. You are giving a precise, detailed series of numbers, sometimes maybe an address, maybe a GPS coordinate, maybe latitude and longitude sort of grid coordinates, right? But you are giving a representation of your location that can be very, very precise, right? And is represented generally numerically in some way. One of the ways that we're used to seeing this, and that's shown on most every map that you'll look at, is through the system of longitude and latitude that create a kind of grid around the Earth. These are lines that have been sort of superimposed over the surface of the Earth to help tell your location. Longitude, or sometimes referred to as meridians, are arcs, kind of semicircles that run from pole to pole, from North Pole to South Pole. And although they run sort of north-south, right, in a straight line from the North Pole to the South Pole, they are actually helping you to measure your distance sort of east and west of the zero line, the prime meridian. The international date line is sort of opposite the prime meridian at 180 degrees longitude. Generally, we'll talk about sort of how it has some zigzags in it for the most part. So 180 degrees going, easterly from the prime meridian, and 180 degrees around going to the west of the prime meridian, both ending up in basically the same spot, that international date line. We can also superimpose another set of lines of latitude or parallels to help complete this grid that we've laid over the Earth. Lines of latitude are also called parallels because they actually sort of run parallel to each other, right? Lines of meridian or longitude are all intersecting eventually, right? Even though they might look sometimes like they're running parallel in portions of the map, when you look on a globe, you will see that all those lines of longitude converge at a pole, right? They intersect at a single point. Lines of latitude do not, okay? They run parallel to each other and are thus different sizes. The lines of latitude run in an east-west direction, right? If you're looking at them on a map, but they help you sort of measure your location north and south of the equator, okay? From 0 degrees at the equator to 90 degrees at the highest parallels, and then 0 degrees and 90 degrees to the south. These can be further divided, right? Both lines of longitude and latitude into minutes, shown with a little sort of quote mark there, or kind of an apostrophe, and seconds generally shown with the apostrophe, or excuse me, with the quote symbol there. And you would do this to give yourself even a finer level of detail on your actual location. All right, and so here they are once again, okay? Lines of latitude running to the left and right, or sort of east-west kind of direction, but it's helping you tell your location from that main line of the equator that is at the center point of the Earth, right? So you're going to see it as either 0 to 90 degrees north or 0 to 90 degrees south, but you won't see something like 180 degrees latitude, all right? It's always going to be between 0 and 90, north or south. And then longitude, likewise, you have a starting point, I guess, of 0 that runs through Greenwich, England, and 180 degrees east and west of that, right? Ending up at 180 degrees longitude, or the international dateline. You put those two together and you get this grid pattern over the Earth that lets you get a precise location for any spot, a mathematical location. Now, when you start drawing lines of latitude and longitude across the Earth, they subdivide the Earth into all kinds of different sections. And it's worth pausing on this section of the lecture. I won't read every single one to you, but familiarizing yourself with those lines, as you might see them throughout the course in various ways. And it's another way that those lines of latitude or longitude can be used to isolate certain regions of the Earth and not just your location. Time zones are related both to location and to lines of longitude, all right? As you vary your location on the planet, the time zone you're in will vary as well. Time zones are basically the result of recent technological advances, right? Relative to the scale of history, but recent technological advances like the ability to travel about the Earth faster than people ever have before, where you might arrive at very distant locations in the same day, right? Or the ability to communicate across these giant stretches of space where, again, you're communicating with people on the other side of the planet, where because we're flying through space on this rotating ball of the Earth, it might be closer to the end of their day. They might be losing daylight on one side of the Earth while your morning is just getting started on another. So time zones are one of the ways that economic situations, political situations can be expedited or made a little bit more convenient for people across these big distances to interact with each other. So what they actually end up doing is that time zones divide the Earth into 24 regions. Each of those regions about 15 degrees of longitude in width, and totaling 24 different sections around the Earth, right? You put that together, you get 360 degrees all the way around, with each time zone representing essentially 1 hour, although there are local variations in a couple countries, places like India, or in places, regions of certain countries like Newfoundland in Canada, that are not necessarily divided by 1 hour, but by half hours for local economic or politically convenient reasons, usually. Notice on this map that there are other kind of standouts. One, you can see India, a big country that maybe ought to be in 2 different time zones, is sort of united on its own local variation. China as well, which should span several different time zones, is all united on a standard Chinese time zone, right? So even though the distances in China are similar to East Coast, West Coast in the United States, all the clocks will generally read the same time throughout China, right? There is no difference on the clock from the eastern or western portions of China. versus the United States, which on the, sort of continental United States, the contiguous United States there span 4 different time zones, right? Our Pacific, Mountain, Central, and Eastern time zones. An important part of talking about time zones is talking about the international dateline and some of the interesting things that happen there. Time zones split the Earth into 24 different hours of time, right? And as you travel away from the, zero line of longitude and the 0 hour of Greenwich Mean Time, you will eventually, if you're traveling fast enough, get to a point where you can start to circle the Earth, and with time zones not having anything to stop you from doing it, have this ridiculous situation where you might cross into tomorrow, right? And begin to sort of run your clock ahead or behind, depending on the direction you're traveling. The international dateline is what stops that from happening, what essentially allows you to reset the clock and keep the entire world more or less within a single 24-hour period. So what that means is when you cross the international dateline, the day and the date are going to change to keep you sort of in sync with the rest of the planet. If you cross it traveling westward, traveling to the west, the day is going to go forward by 1, right? Or the date will sort of increase by 1. If you cross it traveling eastward, then the opposite is going to happen, right? The day and the date are going to sort of go back by 1, but all to keep everybody within a 24-hour time period. Now, one of the big problems of this is that for the most part, or entirely, the starting point of all this, 0 degrees longitude, is an arbitrary spot on the Earth, right? The equator, 0 degrees latitude, is actually sort of the center point between north and south, right? It is the largest area of circumference around the globe. It has some scientific relevance. Lines of longitude don't necessarily, right? 0 degrees longitude was an arbitrary spot picked by sort of the first people to kind of map that out on a global scale. But it could have run through anywhere, okay? 180 degrees longitude is the same. It's an arbitrary location. What is kind of convenient about that international dateline, though, is that it's mostly running through a relatively uninhabited part of the Earth, right? There's a lot of island chains out there, but not these big continental land masses. But in a sense, this can make it even more inconvenient or present unique problems. As you can see on this map here of these Pacific Islands, a lot of these island chains cover thousands of miles, right? And that puts them in weird positions where technically they would be covering several different time zones. Some of them have gotten around this by putting themselves in a situation like I mentioned with China earlier. Even though they're maybe technically in several different time zones, these island chains might all be on one. Some of these island chains, like the chain of Kiribati, were in a position where some of their islands were on one side of the international dateline and some of their islands were on the other, which means that as they try to communicate, you're trying to do business with people that are on another day than you, all right? And you essentially would reduce the amount of days that you could even do business to about 4 days a week because you're going to kind of lose a day with the other half of your country. Kiribati's solution to this was to simply move the international dateline as far as they were concerned about 2,000 miles to the east, making them, not exactly follow standard time zones, but keeping them, the people of Kiribati, all on the same page as far as the date goes, all right? And that makes business and convenience, travel, all that stuff a lot more convenient there. It also, marketing-wise, makes them the first country to see each day's sunrise. Now, there have been several other island chains that have followed suit with that as well, but that is why we say the international dateline generally follows 180 degrees, because it does have some zigzags around some of these islands. The next part of this lecture will finish up by looking at the ways and tools that geographers collect data about locations throughout the Earth, all right, with the emphasis being on the tools and how that stuff is transformed into data. Geospatial data, right? Data about the surface of the Earth, or things arranged across the space on the surface of the Earth. One of the most important tools to a modern geographer is GPS, okay? The Global Positioning System. We use it every day to help figure our location within our communities, right? Or navigate from point A to point B. What it is actually, though, is a system of satellites and receivers, all right? As of June 2020, there have been 75 GPS satellites launched, 31 of them currently being operational, 9 of them held in reserve in case one of them breaks or things like that. And a whole bunch of others have been retired or lost to failed launches, etc. But there are a whole bunch of these satellites arrayed in geosynchronous orbit, right? So they're sort of always in a hovering around a certain spot of the Earth. And they help to sort of triangulate your location, right? By 4 or more of these satellites communicating with a particular receiver, they help to figure out the location of that receiver relative to the location of all those satellites, right? And pinpoint your location on Earth, giving you a mathematical location or an absolute location that can be represented in GPS coordinates. Other ways that geographers study locations of the Earth is through geographic information systems, like maybe some of the ArcGIS tools that we messed around with in some of our class activities. GIS is a computer system that allows spatial data, usually in the form of maps, to be collected, recorded, stored, retrieved, organized, manipulated, analyzed, and displayed, any or all of those together. Most commonly, GIS is going to be used by us in class or even by geographers to create layers of map data that can be laid on top of each other to show relationships between different kinds of information, right? So the visual on the left there shows all kinds of different map layers that you might isolate to distinguish information about a given area. Whether that's a topographic map that helps show elevation for a certain area, a map that shows land parcels and who owns what, or zoning maps that help you to see what parts of a town are designated for what kinds of business or something, where certain wetlands might be located, or soil types, etc. Right? You could see the value in maybe being able to collect some of those layers of information and aggregate them or collide them into a single map. Remote sensing refers to the acquisition of data about the surface of the Earth, either from a satellite orbiting the planet or from other long-distance methods. Generally, it's going to often involve the collecting of images, maybe from, like we said, a satellite or a drone flying very high or some other high-altitude aircraft, but it might be collecting other kinds of data, climate data, or elevation information using lasers or things like that. It doesn't have to be strictly images. But the idea is that this data is being collected remotely, right, from some long distance method. One way of looking at this kind of information that you might be most familiar with would be Google Earth, which you've probably messed around with a lot on your phone, seeing satellite images overlaid with the city or the areas that you're traveling to. Now, this won't work on this presentation, but if you are able to open up this presentation on your own on our website, you will be able to watch this clip that shows 5 examples of some of the human activities you can see through sensing the Earth remotely, right, by using remote sensing. Geographers use all kinds of maps to learn about and study locations across the earth, right? And the variations in those locations. Whether those are physical maps or online maps, like some of the ones that you've, again, sort of explored in class, whether that's interactive maps like the 270 to Win website or some of the cartograms you looked at the Bouncy Maps website. Online maps are a valuable modern tool for geographers to study location data across the globe. Polls and surveys are another method that will reveal locational information. And polls and surveys can produce data that can be broken down into some scientific terms known as quantitative data or qualitative data, and we'll explain each of those. Generally, what you'll get with polls and surveys is quantitative data, all right? Data that is capable of being measured and expressed with numbers that can be quantified, right? Like anything sort of statistics related, you're going to need a lot of subjects to make that data reliable and useful. But a good example of that might be the kinds of exit polls that are taken after or sort of during our national elections, where people are asked who they voted for as they leave the polling booths, right? Who did you vote for? And maybe some other demographic information, right? Your gender, your age, your ethnicity, and things like that. And that is how the media, various news channels and things like that, are able to try to predict a winner despite no votes actually officially being counted at that point, on election night. So polls and surveys render locational data, maybe like exit polls for geographers. Another way that data can be collected by geographers at precise locations is through field observations, or what's just simply known as field work, where a geographer is actively sort of going to a location and observing, recording, and collecting data on site. All right. And that can include very official kind of land surveys or something more informal, photos, sketches, interviews with local people in that area. But that is where a geographer is sort of putting boots to ground and doing work in their field, sort of in the field, if that makes sense. Now, these field observations can collect both kinds of data, right? Data that is quantitative, like from the slide before, from polls or surveys, where they are collecting the kinds of things that you can measure, maybe tree loss or maybe counting up a certain species of animal in an area, right? Recording that through photographic evidence or just logging records of what they see. But this can also take the form of data known as qualitative data. And this is information that's not as easily represented in numbers, right? These are things like you might find certain diary accounts of geographers, open-ended questionnaires, documents, participants, and their personal accounts from an area. So information that's a lot harder to analyze and represent visually, but is still really important to geographers to sort of understanding what's going on in the areas that they're studying. A great quote that I saw from one of the textbooks I've used in the past is that this kind of field work of observations and collecting that qualitative data is essential to geographers to understand the social reality of individuals, groups, and cultures as nearly as possible as its participants feel it or live it. And you get that through that hard to quantify qualitative data. And finally, we can talk about the census, right? Which is, in the United States, the complete numbering of our population, right? Or as close as we can get it. In the United States, we do it very consistently. Every 10 years since the start of our country, we have conducted a very accurate census. We are in the process, as this is a census year, of acquiring that data right now. Although those efforts have been hampered a little bit with the COVID situation. We will talk in later units in our political geography unit, for example, about why it's so essential to our system to collect census data every year. But just suffice it to say that all kinds of information is collected, okay? On top of simply population, we look at all kinds of economic information, whether that's household income, cultural information like the distribution of ethnic groups, or levels of educational attainment, all kinds of information. Other countries might not be as consistent in their census keeping, right? Either because of conflicts or lack of funding, or just maybe not having it scheduled to take place as regularly as we do, because of the political reasons that we do it. All right, that concludes this fourth lecture on the idea of location in geography and some of the tools geographers use to collect that locational data, and some of the ways of finding our mathematical or absolute location on the Earth. Thanks a lot, guys, and talk to you again soon.